Hello and welcome to the cancels. So next we have 5 toddlers pulling on a toy. You want to know the net force acting on it for the first part of the problem. So in order to do that, you want to draw a free body diagram. To do the free body diagram, you draw the object as a little dot, or you could draw a square, whatever you want. And you draw all the forces as vectors. So let me do that. So here we go. Just assume all of these units are in newtons. So you have 20 north, 13 south, 18 east, 7 more south, and then 20 north. So what happens is all the north vectors and the south vectors cancel with each other. So what you have is 20 north, and then 7 south and 13 south. So minus 7, because pulling 7 south, and then 13. You're also moving south. Let's say the north is positive, south is negative. What happens is you end up with 0 net force going up and down, so you can just get rid of these. The only force vectors that we have not canceled yet are the left and right force vectors. So you have 20 left, and 18 right, or 20 west and 18 east, right? So then you get 20 minus 18, and you get 2. So these cancel out to end up being 2 this way. 2 newtons. So your final force is going to be 2 newtons, and it's going to be directed to the west because that's the only one that we didn't cancel. So 2 newtons west. To figure out the acceleration, you have to use the equation from Newton's second law, which is F equals ma. So you got F equals ma. Now the force, you just figured it out. The force is 2 newtons, right? So 2 newtons equals the mass, which is up here, 1.5 kilograms. 1.5 kilograms times the acceleration, which is what we don't know. So that means that the acceleration, doing some algebra, is going to equal 2 over 1.5. And that gives you 1.33 meters per second squared. 1.33 meters per second squared. And then this is 2 newtons, 1.5 kilograms. So that's your answer. Down here, circle 2 descriptions for the velocity and 2 descriptions for the forces. So velocity, if it is a curved line, then it's going to be a changing velocity. If it's curved like this, or like this, so that it gets more steep as time goes on, like you start off with a very low slope, like flat, and you end up with it going up or down, then it's going to be speeding up, because the slope is getting farther away from 0. If it looks like this, or this, then it's slowing down, because you start off with a very big slope, that's a big velocity, and you end up with no slope, or no velocity. So you're going from a high speed to 0 speed, which is slowing down. So here, this is a negative line, and it is constant, because it's not curvy. If it is a constant velocity, then the forces are balanced in an equilibrium, because you have no acceleration. Curvy line is the same thing as acceleration. So if the line is curvy, then you have acceleration, and if you have acceleration, then you have an unbalanced or not 0 net force. So right here, this is a negative slope, so negative velocity, and it's getting faster because you start off with low slope and you end up with a high slope. Well, very negative is the same thing as high, let's say. If it's a curvy line, then it's unbalanced and it has a not 0 net force. These bottom two are actually synonyms. So every time it's unbalanced, you will also have non-zero net force. Every time it is balanced, it will be in equilibrium. So here the velocity is negative and it's getting slower because it starts off with a slope and ends up without one. The forces are unbalanced and non-zero. Right here it's a positive slope and it's getting slower. The forces are unbalanced and non-zero because it's a curvy line. That means it has acceleration. Here it's positive and getting faster. If it is getting faster, then it has unbalanced or non-zero forces. Here it's constant and positive. And these forces are going to be balanced and in equilibrium. The bottom ones come as a pair. Let me quickly remind you about Newton's law. Newton's first law says that an object in motion tends to stay in motion and an object at rest tends to stay at rest. It's called the law of inertia. The second law says that force equals mass times acceleration. Basically, I'm paraphrasing it. And the third law says that every action has an equal and opposite reaction. So whenever you have objects that want to keep moving or that don't want to start moving, you're dealing with the first law. Like in this case, where you pull a tablecloth out, but the plates don't want to move. Now, whenever you have a problem that talks about numbers, you want to deal with F equals ma. Numbers are generally going to talk about the forces that you get from particular masses and accelerations. So here you pull a wagon with 20 bricks and it goes half as fast. Well, to figure that out, you got to use the formula F equals ma to see the exact relationship between these things. So second law. The fish swims backwards, or the fish swims forward by pushing water backwards. So you have the water being pushed back, the fish being pushed forward. That's a pair of action-reaction forces. This one, a third as much force leads to a third as much acceleration. Well, those are numbers. Use Newton's second law to deal with the numbers. This talks about an astronaut moving something forward and then she flies backwards because of an action-reaction pair. That's the third law. If the Earth stopped spinning, you would keep flying. You would, fly off because the Earth is spinning and so you're moving right now. If the Earth stopped, you would want to keep moving. So that's because of the inertia that you have. First law. When you punch a wall, it hurts your hand because the wall punches you back. That's the third law. And then F equals ma, that's the second law. Down here, formula analysis. So the way that you do formula analysis is you write down the equation, in this case F equals ma, you change the particular variables into the factors that you're changing them by. If it doesn't change, it's a 1. And then you just evaluate the expression to figure out the factor that your unknown variable changes by. I'll give you an example. Let's say that you have an F accelerating, so a force is accelerating a mass with an acceleration a. Later, the same mass is accelerating with a new acceleration 100 times larger. So I would say the same mass, so I replace that with a 1, and then the acceleration is 100 times larger, so that's 100. So what this gives you is that it says F equals 100, but that doesn't mean that the force is 100 newtons. That means that it is 100 times bigger than it used to be. That's how we do formula analysis. So the force is 100 times what it used to be. Now, if the acceleration was only 1/3 instead of 100 times what it used to be, you do the same thing, right? F would be 1 times 1/3, which is a third. So the force is 1/3 of what it used to be. Now, this is a little bit different because you want to know about triple the mass, what would the acceleration become? So you have F equals ma. Now, the same force, so the force is a 1. Triple the mass, so the acceleration becomes a 3. Triple the mass, so the mass becomes a 3. And you want to know what a is, right? So you got to divide by 3, these cancel. And you get the acceleration is 1/3 of what it used to be. So the acceleration is 1/3 as much if you triple the mass. The same force is applied to an object with 10 times the mass. What is the acceleration? Well, you got the same force, so the force is a 1. The mass is 10 times, so that's a 10 times the acceleration. So you got to get that alone, divide by 10. And what you get is that the acceleration is 1/10 of what it used to be. So 1/10 times. That's a 10. Acceleration is 1/10 what it used to be. Now, action-reaction statements. An action-reaction statement involves two forces and two objects. It's like I hit the wall, so the wall hits me. It's the force and the result of the force. So if you punch a brick, then the reaction to that force is the brick hitting your hand. So you can see that they're complementary and kind of opposite. An action-reaction force statement for a fish swims forward by pushing the water back with its fins would be that the fish pushes the water back, so the water pushes the fish forwards. And hopefully you know H2O is water. So if a fly swatter hits a fly with 0.1 newtons of force downwards, the fly pushes against the fly swatter with exactly the same amount of force, upwards. So 0.1 newtons forwards. Finally, the last action-reaction pair, you have a soccer player kicking a ball. So if the foot hits the ball, then the ball also has to push back or hit the foot. Next, we got free body diagrams. A free body diagram, the definition of a free body diagram, is a picture of or a representation of all the forces exerted on a particular object. Next, you got to draw one. So you have a soccer ball rolling to the right, and the ball is slowing down because of friction. So you have a ball, and on the planet Earth, you're always going to have gravitational force going down and normal force going up. So gravity, normal force. Now, it's moving to the right, but there's no force to the right because nobody's pushing it. The only force acting on it is actually the frictional force opposing the motion. So this way, you have 1.5 newtons of friction. Even though it is moving to the right, it's slowing down, so the force is opposed to its motion. To figure out the net force on the ball, you got to realize that the gravitational force and the normal force are going to be exactly opposite, so they'll cancel it out. So the net force on the ball is 1.5 newtons. That's it, because the normal force and gravity cancel. Now you want the acceleration on the ball, right? You got F equals ma, and you know that the accelerating force is going to be the only net force on it, right? Which is the friction. So 1.5 equals the mass, which is 0.4, times the acceleration. So you do, to get the acceleration, divide by 0.4. So you get the acceleration is 1.5 divided by 0.4, and that gives you 3.75. So 3.75 meters per second squared. That is the acceleration of the ball as a result of the frictional force. And we got another one, almost exactly the same problem. A student is pushing a 5 kilogram book with a 40 Newton force to the right. So we have a book. He's pushing it with a 40 Newton force to the right. And it's sliding to the right. The frictional force is half the book's weight, so we got to figure out the book's weight. We also know that whenever anything's on the planet, you have gravity going down, and you have normal force pushing up. So to figure out the weight, which is going to be this force right here, the force of gravity, which is also going to be this normal force because the gravity and the normal force cancel each other out. That's why you don't fall through the floor. Oop. You got to use the formula F equals ma. The force of gravity is the weight, right? So the force of gravity, that's what we want to find, we can equal the mass, which is 5 kilograms, times the acceleration. And the acceleration of gravity is always going to be negative 10, right? So negative 10. So we get the force is 5 times negative 10, which is going to be negative 50, but the weight is just the magnitude of that force, actually. We assume that the weight is downwards, so we don't need the negative. So the weight of the force is going to be 50 newtons, which means that the normal force is also 50 newtons. 50 newtons, let me put that, 50. And we got that the frictional force is half of the weight, so the frictional force is 25 newtons, like that. Great. So this is a free body diagram. And now we got to know the book's acceleration, right? So you got F equals ma to figure out the acceleration of this object. And the force that we do here, this is the net force after you cancel everything out. So gravity and normal force, they cancel. So this and this cancel each other out. We have 40 to the right and 25 to the left. So what this ends up with is 40 minus 25. That's what we get to the right. And that is 15 newtons to the right. So the total force, after you cancel everything out, 15 newtons this way. So I got F equals ma. F is 15 newtons equals the mass of the book, which is 5, times the acceleration. So 15 divided by 5 is 3. So the acceleration is 3 meters per second squared. Great. 25. Draw a free body diagram for a skydiver. So obviously you have gravity. That's why skydivers fall, pulling them down. That's gravity. And if you include air friction, then you reach something called terminal velocity, which is where you don't get any faster. That happens because air friction, or the air resistance, is pushing up with you just as strongly as gravity is pulling you down. And it makes sense that there's air pushing up on you, right? That's why your people's hair whip around in the wind when they're in wind. So you have gravity going down, and you have the force of air resistance pushing you up, and that's it. One arrow down, one arrow up. We are almost done. 3 more problems. So what do you call a pair of forces that are created in accordance with Newton's third law? For example, if you stomp on the ground and the ground pushes up on you, what is that called? So this is a vocab word you got to know. It's called an action-reaction force pair. You have to know which one of Newton's laws is called the law of inertia, which is a little nickname. It's the first law. So Newton's first law is the law of inertia. And then finally, what has more inertia, a 100 kilogram rock or a 3 kilogram kitten? Well, inertia is how hard it is to move or change the motion of something. It's harder to move it if it's heavier. Another way to say that is it's harder to move it if it's more massive. So the one with more mass will have more inertia. So it will be the 100 kilogram rock that has more inertia than the 3 kilogram kitten. Great. That was long. Hope it was helpful. Thanks.